Hi, today we are going to look at calculating areas under curves. So we know how to calculate areas of squares, rectangles, triangles, parallelograms, trapeziums, circles. Um, those are the main shapes. A few other shapes you can work out by splitting it up. But when you get something like a parabola and you want to find the area underneath this is approximately a trapezium, I suppose you could say, but it's not exactly. How can we exactly calculate this area? Well, the first thing we're going to do is just estimate it. So I suppose there's two ways you could estimate it. You could, first of all, do what I just said and make it into a trapezium. Um, and you could work out these two parallel sides. A bit awkward because actually you're even going to be estimating that, but you could use that to work out the area of trapezium. We're going to do something a bit more basic, but actually it's going to be more accurate. We're going to return to counting squares because we've actually got a square grid on here. So what I'd like to do is just pause the video, count the squares, and get an estimate for this area. All right, I'm going to join in with you now. So I count 1, 2, 3, 4, nearly 5. If I also include this little bit, and I think I've got 5, 6, 7, 8, 9, 10, 11. That's pretty much 12. I reckon this is 13 if I combine it with that bit. I think 14 if I combine it with this one. And these two, I reckon I can just about say that gives me 15. Okay, why have I done that? We learned about area a long time ago. Well, there's another way we can calculate the area, and it's exact. And you're just gonna have to roll with it at the moment. But this is what we're gonna do. We are gonna do the integral of x squared over 10 with respect to x. What am I gonna what else am I gonna do? I'm gonna put a little 8 up here and a little 4 there. This is called a definite integral. We're going to do something with those numbers. Before we do these things with the numbers, I'm going to integrate it. So I'm going to raise the power by 1, divide by the new power. So I'm going to divide by 3. That's going to mean I'm dividing by 30 overall. I'm not going to put a C in for the moment. Okay, I will talk more about that, but for the time being, I'm just going to put a big square bracket around it and a little 8 here and a little 4 here. I'm just introducing some notation. This is how you always do it. We've done the integral, we've got our result. I've not put the plus C in. We'll talk about that as I said. I put an 8 and a 4 in, and what I now do, coming over here, is I actually just substitute in the number up here, first of all. So 8 cubed over 30, and then I subtract this one here, minus 4 cubed over 30. So this is me doing a definite integral. Hopefully, you'll have a go at it as well. 8 cubed over 30 minus 4 cubed over 30. What do we get? We get 14.93 recurring. Compare that with our 15. Actually, what integration can do is calculate the area under a curve. This definite integral allows you to do that. We've counted squares and we have done it exactly, and we're pretty close with our estimate for 15, but we don't want to be counting squares all day. We want a much quicker and precise method. Now this is, wow, I can't believe it. Integrating is not just an inverse operation of differentiation, it has a massive application. areas, and from that, you can go into other things. You can go into volumes and surface areas, and there's a whole branch of mathematics. We're only going to touch upon this this year, and in the second year, you'll carry on with areas. But if you carry on studying maths, you'll find out it is unbelievable how useful it is. But first of all, how does this give you an area? And the first thing I'm going to say, actually, just as a little, not rigorous, but helpful scenario, is if you've ever drawn a speed distance time graph, then one thing, do you know what, when you do it earlier on, you often sort of have straight lines and stuff like this. Maybe it looks like that, for example. One thing you learn is that the gradient is the acceleration. But what is the gradient? It's just dv by dt. So that makes sense, doesn't it? From what we've done on differentiation before. So yeah, that's one thing. And then one other thing that you study is that the area underneath the graph is your distance or displacement if you're using velocity. And you just sort of accept that, I suppose, without really questioning it. But we know that ds by dt is equal to v. The rate of change of distance with respect to time is speed, or the rate of change of displacement with respect to time is velocity. So from that, you can sort of see it's going to make sense, isn't it? That s is the integral of v with respect to t. Obviously, again, this is assumed, this is just said that, oh yeah, the area under the graph is the distance, and you've had to accept that. But you can see if that is true, then it follows that s is the integral of v with respect to t. Okay, that was just like one example where you might have seen it before. Let's do it a little bit more rigorously now. So I'm going to imagine I've got any kind of graph. Let's say it's y equals f of x. And I want to calculate like a large area, say this area here. What I'm going to do is I'm going to split it off, and I'm going to say that this is x, and then this is just a very small part of the area that I'm interested in finding, and I'm going to say that this point here is x plus h. Okay, we've used this before when we've done differentiation, and then do you know what? I'm going to backtrack. We have used h, but another thing you can use is delta x. So we used delta x like this. This means a big sort of change, fairly big change in x. This little delta means a small change in x. So we're going to use that, and that's going to mean that this here is a small area. It's delta A. It's not delta times A, it's delta A, meaning a small area. Now, why is that useful? I can say that my delta A is approximately equal to f of x, the height of my rectangle, multiplied by the base. Now, the base is just going to be this delta x. So why is it approximate? Because actually here the height is f of x, but here it's f of x plus delta x. So I'm sort of basically making a rectangle, and it's not quite the same. But if I make delta x small enough, and I can choose to make it small, then it's going to be pretty good. And maybe you can see where this is going. We're going to let delta x become infinitesimally small. We're going to take a limit to sort out this calculate this area. So I can then write that delta A, I'm allowed to divide. I can say that delta A divided by delta x is approximately f of x. And now comes the calculus bit. I'm going to leave a bit of space here. So we can write we can take the limit as delta x tends to 0, and then this is going to equal dA by dx. That is my gradient, and that is going to equal f of x. So it's all going to match up exactly when I do that. And if that is true, we can then use what we did in previous lessons. If I know the derivative is equal to the function, then I can integrate and I can work out the area. The area is going to be the integral of f of x. So I've shown it more generally than when I did that speed time graph or velocity time graph. I've shown it's true for any graph. Now, I haven't shown it as rigorously maybe as some mathematicians would like. I'm just sort of giving an idea of what's going on here. Something I've also not done is I've not really talked about where these values come from. But if I want to work out the area between two x values, then I need to put in an a and a b. It's going to have to accept that one for the time being. But this allows me to use integration to calculate areas. Here's a little summary of what I've said. Yeah, they use delta x as well, and this is what you need to be aware of then. This formula here, okay, and this. The area between a positive curve. We'll talk more about the positive curve and what happens if you get a negative curve later on. Another lesson. And the lines x equals a and x equals b. Okay, these are, I've cut them off, but here's a and here's b. Then the area is given by this, where y is f of x, where y equals f of x is the equation of the curve. We're going to do some examples of that. Before I do that, I just got one other comment. This basically explains the notation for integration, because what I am doing is, without really doing it, I'm splitting my curve up into lots of different rectangles. Each rectangle would be f of x multiplied by this little dx. Like I'm imagining these rectangles are infinitesimally thin. Now, all these f of x is going to be different as I go along. So I suppose I might say I might say that each individual one is xi. What I am doing is I'm adding all of these up. I am using a summation to do that, and I'm summing it from I equals, say, 1 up to whatever my value is, n. I suppose as I make dx like it's infinitesimally small, technically this I'll have an infinite number of summations. I'm not too stressed about that. I'm just trying to show where this notation comes from. We have a summation, and we're adding lots of rectangles together. Technically, I should use a delta hex here because I haven't let it become infinitesimally small yet. But once I do, then I write the dx, I get rid of this I don't worry about writing that, and I change this summation into this summation. This symbol, which Leibniz came up with, is simply a summation notation, essentially, but now I'm summing infinitesimals. So this actually strongly links into other topics. And you might have been questioning why write this for integration, but that's what Leibniz came up with, and it does make intuitive sense, I think. So we are then, instead of summing from I equals 1 up to n or whatever, we sort of say that we're summing between x equals a and x equals b, and we're adding up all these rectangles. I hope that clears up the notation a little bit. Okay, on with some examples. Okay, so I've spent quite a bit of time talking about integration and how it can be used to calculate the areas under curves. These are called definite integrals as opposed to indefinite integrals. So as soon as you start writing limit, we call these limits of your integral a and b, then you are dealing with a definite integral. Okay, we're going to do 3 examples. First thing we're going to do is we're going to look at y equals x. Find the area enclosed between y equals x equals 2, x equals 5, and the x-axis. That is this area here. Do it using integration and by calculating the area of the trapezium. Okay, I think let's do the area of the trapezium first actually. So we've said it's between x equals 2 and x equals 5. And then we want to work out the area of the trapezium. So we've got a height which is 3. We're going from 0 to 2 because of this line y equals x. So this top part of the trapezium is going to be 2. And we're going from 0 to 5. This point here is going to be y equals 5. So this length here is going to be 5. Okay, so then the trapezium, if I do that first of all, is going to be a half 2 plus 5 times 3. That's going to be 7 times 3, 21, divided by 2, 10.5. We're not working in centimeters or anything here. Technically, like it's a unit, 10.5 units squared, but you don't really need to write that. Just be aware of it. Occasionally, you could have some sort of measurement. I mean, you can, it will be useful for measurement situations, but right now we're just interested in working out the number. Okay, then the exact, well, not the exact because that is exact, but the integration way will be to do the integral of x with respect to x between 2 and 5. That's going to give us these square brackets. We always do that. Please do that. Half x squared, increase the power by 1, divide by it. I just brought it down as a half instead of x squared divided by 2. Oh, this time I'm going to put my plus c in. Yeah, I didn't want to before because I didn't want that to be the focus. But this time I'm going to talk about whether we need it or not. 5 and 2. Okay, and then as I did before, I'm going to substitute the 5 in. I'm going to get a half times 5 squared plus c. I'm going to put that in a bracket, and then I'm going to minus a half times 2 squared plus c. Running out of space here, just bear with me. This is my second example. Okay, bring it down a bit. Okay, I can get rid of these brackets. I'm going to get 25 divided by 2, 12.5 plus c. And then I needed a bracket around here because I'm going to minus my 4 squared half of that, 2. And then I'm also going to minus my c. Now this is why we don't need to include c, because it's always going to cancel out. So I didn't bother with it on this first example, and you don't need to bother with it. You can put it in if you want, but you're just wasting time. Because we're adding c here, but we're adding a c here, it's not going to matter what c is. So I'm just left, so I can just basically not put that in, not put that in, not put that in, and it's absolutely fine. And then I get 10.5, which is the same as when I did it for the trapezium. So further evidence that I'm not making this up. Good. Okay, another example. This time I don't have a trapezium, so I can't work it out using that method. I'm going to have to just stick with integration. I'm just leaving enough space for my third example. Okay, find the area shown shaded in the diagram under the curve y equals root of x from x equals 1 to x equals 4. Right, this is the third time you've seen it, so hopefully we can get straight into it. It's going to be the integral of x to the half. We always write our indices down with respect to x between 4 and 1. Add 1 to the power. Divide by 3 over 2, which is the same as timesing by 2 over 3. Don't bother with the plus c. 4, 1, substitute in 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. Okay, challenge here. Let's do this without a calculator. You might be able to immediately recognize that this is going to be a nice number. We're going to be taking the square root of 4, give us 2, and then we're going to be cubing it. So it's going to be 2/3 times 8 minus 2/3, because 1 to the power 3/2 is just 1. That's going to give us, well, I've got 8 lots of 2/3, and then I'm minusing 1 lot of 2/3. It's going to be 7 lots of 2/3, or 14/3, or 4 2/3. Let's leave it exact. That's the answer. Does that look about right? Well, the square root of 4 is 2. If I was to sort of do a rectangle, then I'd do 3 times 2, I'd get 6. Okay, it's a bit less than that, isn't it, because of this area here? So that looks about right. You can sort of sometimes just check and see if that looks about right. That looks about 1 and a bit, so I'm happy. Okay, one more example. You can see we're slowly sort of increasing the complexity, and here's the most complex one. I'm not giving you the graph here. Find the area of the finite region between the curve with equation 20 minus x squared in the x-axis. Okay, I'm going to need to do a bit of work to be able to deal with this, because at the moment I've got some axes, but I don't know where it crosses. So the first thing we're going to have to do is find where it crosses. 20 minus x squared equals 0. That's going to tell me where it crosses the x-axis. What I always like to do is basically multiply by -1. X squared plus x minus 20 equals 0. You can imagine like adding both sides by x squared and so forth, but get it so we've got a 1 here. Factorize, it's going to factorize. You can see 5 and 4 are going to work, so it's going to be x plus 5 and x minus 4 equals 0. To multiply to give minus 20, add to give 1. And so we're going to get x equals -5 or 4. Okay, good. So this is a negative quadratic, and we know it goes through -5 and it goes through 4. So it's going to look a bit like, and then it's going to go through 20. Do you know what? I don't actually know that I suspect that the maximum is going to be a bit before. That's not really important to this problem, but let's just try and be accurate. Okay, so that's the fair, that's probably the hardest bit of the question done, to be honest, because you've got to be able to set up your integral. So find the area of the finite region between the curve with equation. So there's an infinite region outside the curve. There's an infinite region under the curve here, but it's got the x-axis. So what we're interested in, finding this area here. Okay, so this is going to be the integral between 4 and -5. Now, I just realized I've not spoken about this yet. If you want to find the area, then you're always going to use the larger limits at the top and the lower, the smaller, the lowest one, negative, for example, 1 on the bottom. If we did it the other way round, then I'd be subtracting the other way around and I'd get a negative answer. And it is sort of possible to get negative answers in your integrals, and you might be asked to work out the integral where you put 5 here and -5 here and 4 here, and you'd get a negative. But if we are working out the area, then we always put the highest one first. That is something I'll talk about a bit more. Right now, let's just get this finished. Okay, so it's going to be 20 minus x squared dx. And we've been practicing these, so that's going to become square bracket 20x minus a half x squared minus a third x cubed. ideally, this is sort of the pace that you're working at now when you're doing integrals. You just, it does take practice, and if you want more practice, put it in, but you should be able to look at x and say half x squared and so forth, same for x squared. Show your working if you need to, but like try and get a good pace going. It shows your understanding. Okay, substitute this in. So 20 times 4 minus a half times 4 squared minus a third times 4 cubed. And then minus, this is starting to get quite messy, 20 times minus 5 minus a half times minus 5 squared minus a third times minus 5 cubed, close brackets. Put that in your calculator. We could try and do it without a calculator, but it's going to be quite horrible. Like with fractions and everything, we know how to, as long as we know how to deal with it. Okay, I get 152 over 3 minus, be really careful with your negatives. That, remember, there's a minus right there. Okay, so then I'm minusing 425 over 6. So that's going to become 152 over 3 plus 425 over 6. Remember, we're always putting a minus here, so if you then get a negative from your integral, which can happen, then you need to do a double negative. Okay, my final answer turns out to be not too bad, 121.5. Okay, there is, if you're using the ClassWiz calculator, there is a way of getting to this step here and just basically putting it in your calculator, and it will just let you know what the answer is. It won't do anything. It will do all these steps for you. I've got a few comments on that. I think that's absolutely fine, especially to check an answer or if you're short of time. However, you need to be able to deal with complicated arithmetic like this, and practicing and being careful is an important skill. So my recommendation is do what I'm doing here, and then if you want, just check that. There will be questions that ask you to, I might have an x in my as one of my limits, and then you can't put it in your calculator, or I might have an unknown in my integrand. I call this my integrand, and then again I can't put that in my calculator. So don't just be lazy and think, oh, I can just always substitute my calculator, it will do it all for me. Something I try and really reinforce when I'm doing maths teaching is just try and do as much as you can without a calculator. Occasionally you might make a little mistake, fair enough. When it comes to an exam, fair enough, you might rely on it a bit more, but it's just, you can do things faster, you can do more complicated questions if you get a good feel for it. You should know what 4 to the power of 3 over 2 is, and do that in 5 to 10 seconds, I would say. That's where you're aiming to get to. Same sort of thing here. I will make mistakes when I'm doing this sort of question. I'm going to check that this one's right before I post this up. You can assume it is if this video goes ahead. But look, I need to just be careful as I go along with my negatives and my double negatives and so on. Okay. Anyway, that's it. We've done 3 examples. They've got gradually harder. You do need to be able to sketch curves sometimes before you do the integral. You can see that as a harder question, can't you? Because we're combining 2 skills, but make sure you can do that. So what I'd like to do is practice. Thank you very much for watching.